What if electricity could flow forever, without losing a single drop of energy? Well, it sounds like a violation of the fundamental rules we observe in our everyday lives. Every time you charge your phone, turn on a light, or use any electrical appliance, a portion of the energy is inevitably lost. The wires carrying the current get warm to the touch, a subtle but constant reminder that even the best conductors, like copper, resist the flow of electricity. This resistance bleeds energy away in the form of heat, a silent tax on every electron that completes its journey. This energy waste is so pervasive, so deeply embedded in our technological world, that the idea of a perfect conductor seems to belong more to science fiction than to reality. And yet, such materials do exist. They are called superconductors, and their discovery over a century ago represents one of the most profound and beautiful moments in the history of physics. These are not magical materials that defy the laws of nature. Rather, they are materials that follow the deeper, stranger, and more elegant rules of quantum mechanics. To understand them is to journey into the cold, quiet world of atoms near absolute zero, where the familiar classical behavior of matter gives way to a hidden quantum order. This is a story about how, under just the right conditions, electrons can learn to cooperate in a way that allows them to glide through a material without any resistance at all. This journey will not involve complex mathematics or sensationalized claims. Instead, we will build the explanation piece by piece, starting with the familiar world of ordinary electrical wires and the reasons they resist current. We will then see what happens when we cool a material down, stripping away the thermal noise that usually dominates its internal landscape. Step by step, we will uncover how electrons, which normally repel each other, can form remarkable partnerships. These partnerships allow them to move as one, a collective quantum state that is impervious to the collisions that plague normal conductors. It is a subtle and astonishing phenomenon. Our goal is to reveal why superconductivity is not a trick or an anomaly, but a direct and predictable consequence of the quantum laws that govern the universe at its smallest scales. We will explore how this perfect flow of electricity leads to even stranger effects, like the ability to levitate magnets in midair, and how these properties are already being used to build some of our most advanced technologies, from medical scanners to particle accelerators. It is a story that showcases the quiet power of scientific curiosity and the remarkable, often counterintuitive world that physics has allowed us to glimpse. So let's begin by asking a simple question. What exactly is electrical resistance? To understand why a simple copper wire resists electricity, we first need to picture what it looks like on an atomic scale. A metal wire isn't a hollow pipe that electrons flow through like water. Instead, it's a dense, highly structured environment. Imagine a vast, three-dimensional lattice made of metal atoms, all locked into a repeating crystalline pattern. In a metal like copper, each atom contributes one or more of its outermost electrons to a collective pool. These electrons are no longer bound to any single atom. They become delocalized and free to drift throughout the entire crystal. This is often called a sea of electrons, a vast swarm of negatively charged particles moving among a fixed grid of positively charged atomic nuclei, ions. This sea of free-moving electrons explains why metals conduct well. When you connect a wire to a battery, an electric field exerts a gentle but persistent push on each free electron. This force nudges them, causing a slow drift from the negative terminal toward the positive. This collective drift is the electric current. It's not one electron racing across the wire, but a slow, orderly procession of the entire sea. The flow of charge powers our world, but the journey is far from smooth. Each electron's path is chaotic and unpredictable. Think of a crowd milling in a hall. Tilt the floor slightly, and the crowd drifts downhill while still bumping around. The drift is the current, the bumping is the problem. This microscopic chaos is the key to resistance. Electrons aren't moving through empty space. They're navigating a packed forest of atomic ions. If ions were perfectly still, electrons as quantum waves could glide unimpeded. But atoms always vibrate. They jiggle in place, and those vibrations disrupt the lattice. These tiny tremors, imperfections, get in the way of drifting electrons and create electrical resistance. The atoms that form the crystal lattice of a wire are not static fixtures. They are alive with motion, constantly vibrating around their fixed positions. This jiggling isn't random. It's a direct consequence of temperature. Any object above absolute zero contains thermal energy. In a solid, that energy appears as vibrations in the atomic lattice. The warmer the material, the more vigorously the atoms shake. Picture a perfectly arranged grid of balls connected by springs, each ball trembling and the whole structure humming with kinetic energy. This motion is a fundamental property of matter. These vibrations are not just a chaotic mess. They travel through the crystal lattice in organized waves, like ripples on a pond. These collective vibrations are called phonons. A phonon is a quantum packet of vibrational energy, just as a photon is a quantum packet of light energy. Think of phonons as tiny propagating waves that carry heat through a solid. Now bring back our sea of electrons. Electrons drift through the lattice under an electric field, but passing phonon waves constantly disturb their path. An electron frequently collides with displaced vibrating atoms. Each collision sends the electron careening off in a new, random direction. This being knocked off course is called scattering. Imagine walking in a crowded hallway where everyone shuffles and bumps you. You get jostled and deflected no matter how determined you are. Your journey becomes a stuttering series of short forward movements punctuated by random collisions. For an electron, the vibrating atoms are that shuffling crowd. More thermal energy leads to more intense vibrations, more phonons, more frequent scattering. That directly translates into higher electrical resistance. Every time an electron collides with the vibrating lattice, something crucial happens. Energy is exchanged. The electron has gained kinetic energy from the electric field pushing it forward, then transfers some of that energy to the lattice. This excites the atomic vibrations even further. The electron's directed motion becomes the random jiggling of atoms. That random motion is, by definition, heat. The battery's energy isn't destroyed. It's transformed into thermal energy that warms the wire. This is the origin of electrical resistance and why devices get warm. Energy is siphoned off, collision by collision, and dissipated as waste heat. But the biggest factor is temperature. Temperature versus resistance gives our first clue towards superconductivity. If heat is atomic vibration and that vibration causes scattering, what if we remove the heat? Cool the metal, calm the violent dance of atoms. As temperature drops, atoms vibrate less and less. The vibration waves, phonons, grow weaker and rarer. Electrons drifting through this quieter lattice travel much easier. Fewer obstacles mean fewer collisions. With each degree down, resistance steadily decreases. But that linear drop raises a question. Keep cooling. Will resistance go all the way to zero? Classical physics said maybe. Reality is far more abrupt and interesting. At the dawn of the 20th century, physicists were locked in a fierce competition, the race towards absolute zero. This wasn't just about cold records, it was about a new frontier of physics, where matter's behavior could change dramatically. Heikki Kamerlingh-Onnes was a pioneer. His light in laboratory led low-temperature physics. In 1908, Onnes liquefied helium, reaching just 4.2 K. That led him ask, what happens to a pure metal's electrical resistance as it gets extremely cold? Classical theories disagreed. Some, like Lord Kelvin, thought electrons would freeze, resistance infinite. Others said resistance would fall and level off, limited by impurities. Onnes tested ultra-pure mercury. He passed a small current through a thin mercury thread. He slowly lowered the temperature into the liquid helium range and measured the voltage across it. Ohm's law, V equals I times R. With I constant, changes in V mean changes in R. As he cooled, resistance steadily dropped. The curve seemed to head to a small, finite value, but he pushed lower, past 4.3 K, watching his instruments. A fraction of a degree more, astonishingly. The resistance didn't level off. It vanished. At a temperature of 4.2 Kelvin, the needle on Onnes's voltmeter, which had been steadily dropping, suddenly plunged. It fell to zero. Not close to zero, but completely and immeasurably to zero. He checked his equipment, suspecting a short circuit or a malfunction. Every wire and connection was sound. It was not a gradual fade to nothing. It was an abrupt, precipitous drop, as if the material had undergone a fundamental change of state, like water freezing into ice. Onnes had discovered a new state of matter. He called it the superconducting state. Below this critical temperature, the electrons were no longer scattering off the atomic lattice at all. They were flowing through the mercury with perfect efficiency, without losing any energy to heat. The chaotic hallway that had once scattered the electrons had suddenly become a perfectly clear and unobstructed corridor. To confirm this extraordinary claim, Onnes and his team devised an even more elegant experiment. If the resistance was truly zero, then a current, once started in a closed loop of superconducting material, should continue to flow indefinitely without any power source to sustain it. They crafted a ring of lead, another material they found to be a superconductor at a slightly higher temperature of 7.2 Kelvin. They cooled the ring below its critical temperature and then used a magnetic field to induce a current within it. Once the current was flowing, they removed the external magnet. Days passed, weeks passed, months passed. The current showed no signs of weakening. The tiny magnetic field it generated remained constant. Later versions of this experiment have been run for years, with ultra-sensitive detectors showing no measurable decay in the current. This was the ultimate proof. Electricity could, in fact, flow forever. The discovery of superconductivity and persistent currents was a triumph of experimental physics, but it also presented a profound theoretical puzzle. While cooling the metal did reduce the atomic vibrations, it didn't eliminate them entirely. Even at 4.2 Kelvin, the mercury atoms were still jiggling with some residual zero-point energy. So, why weren't the electrons scattering off these remaining vibrations? Why did the resistance drop to absolute zero instead of just a very small number? The existing theories had no answer. The sharp, sudden nature of the transition hinted that this was a cooperative phenomenon, something involving all the electrons acting in unison rather than as individuals. It seemed that below the critical temperature, the entire sea of electrons entered a new, highly ordered quantum state, a state in which the familiar rules of scattering and resistance were somehow suspended. But what was the nature of this state? And what was the mechanism that allowed billions upon billions of electrons, which normally repel each other, to suddenly start behaving as a single, coherent entity? The classical picture of individual electrons navigating a shaky lattice was clearly breaking down. A new way of thinking was needed, one that embraced the strange and non-intuitive rules of the quantum world. The key, it would turn out, lay in a subtle and beautiful quantum mechanical interaction between the electrons and the very same lattice vibrations that were supposed to cause resistance. In a stunning twist, physicists would discover that under the cold, quiet conditions of a superconductor, these lattice vibrations could actually mediate an attraction between electrons, binding them together into remarkable pairs. Electrons are famously antisocial. They carry a negative charge, and as the saying goes, like charges repel. Two electrons close together push each other apart with a strong electrostatic force. In 1957, three American physicists proposed a revolutionary idea: John Bardeen, Leon Cooper, Robert Schrieffer. Their BCS theory turned the problem on its head. They proposed the lattice itself, which causes resistance at high temperatures, could mediate a subtle, indirect attraction between electrons. Imagine a single electron moving through the crystal lattice. As it passes positively charged atomic ions, it tugs them slightly with an electrostatic pull. That creates a small, temporary lattice distortion, a region where positive ions bunch a bit closer. That region of higher positive charge lingers briefly, like a boat's wake. The original electron moves on, but the ripple persists. That fleeting positive pocket becomes an attractive spot in the crystal. Now picture a second electron nearby. It gets drawn toward that momentary pocket of excess positive charge. The first electron used the lattice to send a signal, and the second picked it up. That indirect attraction, via lattice distortion, can be just strong enough under very cold conditions to overcome their natural repulsion. It lets them form a delicate, long-distance partnership. This pairing is the first step towards superconductivity. This remarkable pairing of electrons is named a Cooper pair after Leon Cooper, who first showed mathematically how it could happen. It's crucial to understand that this is not like a chemical bond. The two electrons in a Cooper pair are often hundreds of nanometers apart, a vast distance on an atomic scale. They are more like dance partners who are perfectly synchronized, moving across a crowded ballroom floor while always maintaining a connection. Their link is a quantum handshake, mediated by the phonons. The first electron emits a phonon, the second electron absorbs it. Individual electrons are a type of particle known as a fermion. A key property of fermions is that no two of them can occupy the exact same quantum state. But when two electrons bind together into a Cooper pair, the resulting composite object is a new type of particle known as a boson. Unlike fermions, bosons love to be in the same state. Instead of being forced into separate states, bosons are perfectly happy to all pile into the single lowest energy quantum state available. So, as the material cools, they all begin to pair up. All of these Cooper pairs can then condense into a single, massive quantum object, known as a Bose-Einstein condensate. The entire sea of electrons starts to behave as one coherent quantum wave. The current in a superconductor is not the drift of individual electrons anymore. It is the collective motion of this single macroscopic quantum state. Once the Cooper pairs have condensed into this single unified quantum state, scattering becomes almost impossible. There are no single electrons to scatter. To scatter one electron, you would have to break its pair. And because all the pairs are part of the same quantum condensate, you would have to disrupt the entire collective state. This minimum energy required to break a Cooper pair is known as the superconducting energy gap. It's like a protective barrier. As long as the thermal energy from the lattice vibrations is less than the energy of this gap, the Cooper pairs cannot be broken apart. The tiny bumps from the jiggling atoms are simply too weak to affect the condensate. The collective quantum wave of Cooper pairs flows right through the lattice, completely oblivious to the minor imperfections and vibrations that would have scattered individual electrons. This explains the suddenness of the transition. At the precise moment the thermal energy drops below the binding energy of the Cooper pairs, they can suddenly form and condense. The energy gap opens up, and the resistance vanishes abruptly. The phonons, which cause resistance in a normal metal, become the unlikely matchmakers in a superconductor. These pairs then merge into a single, robust quantum fluid that can flow without any dissipation. This allows a current to persist not just for hours or days, but for years, a direct and stunning consequence of quantum mechanics operating on a macroscopic scale. The transition to a superconducting state involves more than just the disappearance of electrical resistance. In 1933, physicists Walter Meissner and Robert Oxenfeld found that when a material becomes a superconductor, it actively expels all magnetic fields from its interior. Imagine a block of lead sitting in a weak magnetic field. as its temperature drops below 7.2 Kelvin. At that exact moment, the magnetic field lines are suddenly and forcibly ejected from the interior of the lead. It behaves as a perfect diamagnet, actively generating its own surface currents to create an opposing magnetic field that cancels the external field within its bulk. And, this expulsion of magnetic fields is the principle behind magnetic levitation. As the material becomes superconducting and expels the magnet's field, it creates an opposing magnetic field that can overcome gravity. The magnet lifts off and hovers in midair, suspended on an invisible cushion of magnetic force. Levitation from the Meissner effect is incredibly stable. The superconductor creates a perfect magnetic mirror image of the magnet above it. Attempts to tilt or drift are met with immediate, self-correcting surface currents that hold it in place. This stable, frictionless suspension visibly manifests the quantum changes inside. The same collective state of Cooper pairs also generates the precise surface currents needed to expel the field and achieve stable levitation. Perhaps the most familiar application is magnetic resonance imaging, MRI. An MRI scanner requires an incredibly strong and exceptionally stable magnetic field. Instead, the core of every modern MRI machine is a large superconducting magnet. It bathes the patient in a powerful field sustained by a persistent current, running coolly and efficiently. At places like CERN, scientists use the Large Hadron Collider to accelerate protons to near the speed of light. To steer these high-energy particles, thousands of immensely powerful magnets are required. These magnets are all superconducting, operating at just 1.9 Kelvin. The persistent currents flowing through the magnet coils create the intense fields needed to bend particle paths. The quest for clean, limitless energy also relies on superconductors. Fusion reactors, like the International ITER project, aim to replicate the process that powers the sun. To contain this plasma, engineers use a magnetic bottle. The coils that generate this containment field are among the largest and most powerful superconducting magnets ever built. Beyond these large-scale applications, superconductors are at the heart of the next technological revolution, quantum computing. Superconducting circuits cooled to near absolute zero provide the perfect environment. They can be engineered to behave as artificial atoms. The same quantum coherence that leads to persistent currents allows these circuits to store and process quantum information. From diagnosing disease to exploring the universe and building the computers of the future, superconductors are not just a curiosity. They are essential tools for a 21st century world. While the BCS theory was a monumental achievement, it was not the final chapter. In the 1980s, a new class of materials was discovered. These were ceramic compounds that became superconducting. At first, around 30 Kelvin, and soon after, above 77 Kelvin, the boiling point of liquid nitrogen. The existence of these materials presents a major unsolved puzzle. The elegant mechanism of BCS does not seem strong enough at these much warmer temperatures. This suggests a different, more robust pairing mechanism must be at play. Its exact nature remains a subject of intense research and debate. The quest to understand these materials is driven by more than just scientific curiosity. The dream is to one day discover or engineer a material that is a superconductor at room temperature. Such a discovery would be one of the most transformative technological breakthroughs in human history. It would revolutionize everything about how we generate, transport, and use energy. A room temperature superconductor is the holy grail of materials science. It stands as a reminder that even in a simple metal wire, there are hidden layers of reality, a deep connection between the smallest particles and the grandest technologies, with many more discoveries still waiting to be made.